So our next task is to be able to identify these local maximum points for a given surface and be able to identify these local minimum points. And somewhere in between there's what's called a saddle point, where it concaves up and then it concaves down. So there's a saddle point somewhere in between. There may be another saddle point somewhere around here where it concaves up and here it concaves down. So so we need to develop a way of identifying these points. So if you look at any local maximum point, let's look at this point here. So let's look at this local maximum point. So when you have a local maximum point, it looks like a hill. So imagine you're at the top of this hill. Well, there's a theorem that says that if you're at a local maximum point, then fx must equal 0 when you evaluate it at the point. And if you're at the local maximum point, fy also equals 0. So and there's a reason for that. If you look at f of x, it looks like this. Hang on. So you've got your vertical sheet of paper going along the x-axis. So imagine your sheet of paper here, where the vertical sheet of paper intersects with the surface. It will look something like this. It will look something like this. So when you look at this sheet of paper flat on, when you look at this sheet of paper, it will look something like this. It will look something like this, and you can see the gradient at the highest point is 0. And then the same goes with fy. So if you look at fy, the vertical sheet of paper along the y-axis will look something like this. And where the surface intersects with the sheet of paper, it will look something like this. So if you look at this sheet of paper head on, it will look something like this. It will look something like this. So if you're at the top of the hill, you can see that the gradient is 0. So another way of looking at this is, imagine you've got a perfectly horizontal sheet of paper which is tangent to the top of the hill. Then in the x direction the gradient is 0. In the y direction the gradient is 0. So there's a theorem that says that if you're at the local maximum, then fx equals 0 and fy also equals 0. So so if we can identify these points in the future, we might be able to head towards a local maximum point. And the same argument goes with a local minimum point. So local minimum points. So let's look at this point here. So if you look at a local minimum, it will look something like this. It will look something like this. And the same argument goes. If you look at fx, it will look something like this. So you can. Oops, hang on. It will look something like this. Hang on. It will look something like this. Hang on. It will look something like this. So if you're at the lowest point here, then you can see that the gradient here is flat. So it must be 0. And then if you look at fy, fy must also equal 0, because if you look at your vertical sheet of paper, where it intersects, it will look something like this. So you can see that the gradient is also 0. So hang on. So whenever you're at a local maximum, so you're at the top of the hill here, it implies that this must be 0 and this must be 0. If you are truly at a local minimum, the lowest point around a closed neighborhood, around a small region, if you're truly at the lowest point, then it must mean that this equals 0 and this equals 0. Okay, and be careful, because the inverse is not true, because if this is 0 and this is 0, it doesn't automatically implies that it's a local maximum or it's a local minimum. Going this way is always true. If you're at a local maximum, then this would be 0, this would be 0. If you're or if you're here, then it also automatically implies that this is 0, this is 0. But going the other way is not true. If this is 0 and this is 0, it doesn't automatically implies it's one of these two. because it could be a saddle point. If you look at a saddle point, you can see that here, if you look at f of x, it equals 0 if you have a saddle point. So this is the origin here. So let's look at a vertical sheet of paper. Hang on, let me draw the vertical sheet of paper. So this is our vertical sheet of paper. So where the surface intersects with the vertical sheet of paper, it will look something like this, which is, so this is the origin. This is the origin. It will look like this. So here it concaves down, but the gradient is actually 0. And then if you look at Fy meaning the vertical sheet of paper in the y direction. So hang on. So where this sheet of paper intersects with the surface, it will look something. So this is the origin. It will look something like this. It will look something like this. So you can see that that the gradient here is actually 0. The gradient here is also 0. Sometimes it could mean it's the saddle point. So in the future, hang on. So wait there. So if you have a hang on, let me think. Sorry, I'm lost. If you have a local minimum, then it means this equals 0, this equals 0. If you're at a maximum, it also means that this is 0, this is 0. If you're at a saddle point, then this also equals 0, this also equals 0. So in the future, we will need to develop a way of identifying where this equals 0, this equals 0. If this equals 0, this equals 0, it could mean this, or it could mean this, or it could mean this. So we assign a name to points where this equals 0, this equals 0. We're going to assign the name critical points. So when you think of critical points, think of points where it's in your mind. Think it's a fishy point where you don't know what's going on. It could be this, it could be this, or it could be this. And by the way, f of x, if any one of these two is undefined, it could be both as well, then it's also a critical point. So in your mind, a critical point is where something fishy is going on and you don't know what's going on. You need to do further investigation in order to identify if it's a local min, if it's a local max, or if it's a saddle. So remember, a critical point is a point where it's fishy, you don't know what's going on, you need to do some further investigations. Okay, and what we mean by a local minimum, what we mean by a local minimum is this. Hang on, so this is your x-axis, this is your y-axis, and this is your z-axis. So a local minimum means around a small neighborhood. So this is your domain here on the x-y plane. So for a small neighborhood, if you put it into the function, it will jump to the surface, and this surface will always be greater than your point AB. So what we mean by a local minimum is that for some small region around that neighborhood, it will always be bigger than the point in question, which is here. So this is what is meant by a local minimum. It means any point on the surface near that neighborhood, it would be bigger than your point here. And a local maximum means a small region around that neighborhood, it will always be smaller than your point. Because if you're really at the top here, any small region around here, it will be smaller than where you're currently located. And then a saddle point means for some xy will be bigger. So currently you are here at the moment. If you're truly at a saddle point, then some region will be bigger than where you're currently is located, and there are some region where it's smaller than where you're currently located. So if you look at this point here, it's smaller than your current location. If you look at this point here, you're actually bigger than your current location. So that's what's meant by a saddle point. Okay. Okay. So in the future, we would develop a way of identifying if it's a max, or if it's a min, or if it's a saddle. Okay. So yeah, I will continue in the next video.